So last time we went over the moon phases, right? And we saw how the changing angle between Earth and the moon and the sun changes the amount that we see that's lit up, right? We also saw that because of the gravity between Earth and moon, it has slowed the moon's rotation enough that the same side of the moon always faces Earth. And so it rotates exactly once every time that it orbits Earth, right? So here we see these different moon phases kind of in a time lapse. Why don't you start by telling me when it's full moon? When does it hit full moon? Imagine that. We all know full moon, right? How often does that happen? Once a month, approximately 29 and a half days. That's where we got the name for month, right? Now tell me the opposite of full moon, and what is it called? Good, it's called new moon, and when is that? Yeah. Now, does that mean the moon is not there? It just means we're looking completely at the nighttime side of the moon, huh? It's completely in shadow. All right, now as we watch this, we see right about here, it's exactly half lit up and half dark, huh? We don't call it half moon. What do we call it? It's not named for the amount that's lit up. It's named for the fraction of the cycle that it has moved through. That's one of the phases, but not that one. It is a fraction. Which fraction of the cycle have we gotten through right here? That's half the cycle right there. Yes. So the full moon and the new moon are the beginning and the halfway point. Right? Right there is a quarter of the way through the cycle, halfway at full moon. And now we're to 3/4 of the way through the cycle, and now we start over. Does that make sense? That's why we call it a quarter moon, even though it's half lit up. Okay? So then the question becomes, which is first quarter and which is third quarter? Third quarter, also called last quarter. So we define the beginning of the cycle as the new moon. Right? Beginning of the cycle is right now. First quarter is here. Second quarter is the full moon. Third quarter is here. And fourth quarter is when we get back to new moon. Does that make sense? It's divided into 4 quarters. Each one takes about a week. Gives us a month. All right, now an easy one. What do we call a moon that looks like that? Crescent moon, right? Here's another crescent moon. On the opposite side, notice the crescent, sometimes on the left you can see it, sometimes on the right you can see it, and that depends on whether it's growing bigger or shrinking, huh? What are the names for growing bigger and shrinking? I know it was 2 whole days ago we wrote this stuff down. Good, waxing and waning. And which one is getting bigger and which one is getting smaller? Waxing is getting bigger. So this is waxing, huh? And then we get to full moon and we're waning again, aren't we? So this is waning crescent. Over here we have waxing crescent. And now, Gabe, what was this one? Football-shaped moon. There's still a crescent of darkness that we can't see, right? We can see most of it lit up, but there's a portion of it we can't. It kind of looks like a distorted football right now. Gibbous. But we have 2 gibbous. We also have waxing gibbous and waning gibbous. Right? So here we go. Waxing crescent, first quarter, waxing gibbous, full moon, waning gibbous, third quarter, waning crescent, new moon. You should be able to do that. Should be able to name these different stages of the moon phases. That's something like if I draw a diagram of the moon and ask you on a test, what stage is this? What phase is this? Or what if I show you a video and I say number 1 right now? Or I just have a photo. Did you name those different phases? Or do we need to practice some more? I like this one because it's that video format. But here's another view that's nice too. Where is it? Here it is. This one has all of the phases in it. You can see them all at the same time. There we go. Okay, so describe, let's just start with the easy one. What's that? Full moon, right? And I think what they're doing, yeah, they are, is the beginning of the month is over here and the end of the month is over here. And that's a lunar month, right? Not a calendar month. This could happen on the 1st, or it could happen on the 10th, or it could happen on the 30th, right? Because the lunar month doesn't match the calendar month. The solar cycle and the moon cycle are out of sync with one another because they're just random things that happen. So here we have full moon, correct? These ones also look pretty full, but can you tell there's like a little chunk missing over here and over here on the right? Yeah? So these ones that are kind of, here's two more, kind of football shaped, what would we call those? Gibbous moons. But which one, the top one or the bottom one, is the waxing gibbous? Growing bigger, isn't it? And then it's getting smaller, so what do we call that one? Waning gibbous. Now, one thing I want you to notice is that if you're really on top of it, you can look at one picture and you can tell if it's waxing or waning crescent, for instance. We know from this picture that the beginning is at the top, so it's growing bigger. So the first 2 rows are all waxing, aren't they? And the bottom 2 rows, it's getting smaller. It's all waning. So how do you tell the difference? Like if you just had this picture, how could you tell it was waning? What's the difference between these 2 pictures? Which side is lit up? When it's growing bigger, it's lit from the right. And this is true in our sky too. And when it's shrinking, it is lit from the left. So right now, today, we're around here somewhere. We're headed for full moon, but we're not quite there yet. In a couple of days, it will be full moon. So we are in what stage right now? Waxing gibbous.
That's tomorrow, right?
Is it tomorrow? I haven't checked. I have an app that'll tell us though. Now, I want you to find on this diagram, let's just number these, 1, 2, 3, 4, 5, 6, like that. Which one is first quarter? Which one is first quarter? Exactly halfway lit up, huh? Yeah, 6 or 7, I would agree. Halfway lit up, right? And it's growing bigger, so that's waxing. So tell me which one would then be waning, which would be the third quarter, last quarter. 5, 10, 15, yeah, 19 or 20, one of those 2, huh? Let me see. And according to this, it says that the moon is going to be full on April 26th. So today's the 23rd.
Oh, that's right.
Yeah, it's a couple days away.
I don't know why I thought.
Yeah. And then the next full moon, it's going to line up perfectly with Earth's shadow. Remember we drew those diagrams that shows, like if this is Earth's orbit right here, the moon is orbiting like this. And the only time we have an eclipse is when it's right in line with our orbit. And that's going to happen next month. There will be a lunar eclipse where the moon moves into Earth's shadow. This month might be a supermoon, which means because our orbit is not a perfect circle, we're a little distorted. We're an ellipse, and so is the moon's orbit. That means that sometimes the moon is a little closer to us than usual. And so it looks a little bit bigger. It's hard to tell because it's only a 10% difference, really. But they call it a supermoon when that happens. So yeah, this month I think is a supermoon. Next month we have a lunar eclipse.
Is that the blood?
Yes, and we're going to talk more about all these parts of an eclipse, but basically what happens, it's almost like this happens all at once in one night over a period of about 6 hours. You start with a full moon, and the moon gradually enters into Earth's shadow. The only thing is, the angle is different. So let me see, I'm going to grab a pen here. I think I'll use black. That would work the best. So this a little bigger. Okay. So what happens as it moves into Earth's shadow, we start off taking a chunk out of it like that. And then as it moves further into the shadow, it does that. And this is one of the pieces of evidence that Earth is indeed circular, because it throws a circular shadow on the moon during an eclipse. And this keeps happening. Of course, it takes a few hours for this to happen. The whole thing is doing this, right? And then you have this little thing. But about here, this kind of starts, and this is going to be too bright. I'm going to use an orange. This starts, the rest of the moon starts to kind of glow a little bit. And it ends up being this coppery color, kind of copper red. Let's see if we can get that. I can't really make it a copper red effect. It's nowhere near that bright. It's kind of a dull red. And that's what happens when it's completely eclipsed, and that's why they call it the blood moon. Now, it's totally in Earth's shadow. So any light that we're seeing on it is actually coming from the sun. But what happens, as the light from the sun hits the Earth throws a shadow, and the moon is in that shadow, completely in darkness. But some of the light comes through our atmosphere, and the atmosphere bends that light, and that light ends up hitting the moon. If it comes through the atmosphere and gets bent, it's refracted into a different color, which happens to be the angle to be red. So that's why they call that the blood moon, when we have a lunar eclipse like that. Does that make sense? Okay, so I would like you to be able to name the different phases of the moon when you see a picture of them. Okay? And Eli, I recorded that class when we did that stuff, and there's an assignment that goes with it. You watch it already?
I watched that.
Okay, so finish the assignment, turn it in, get your points. All right, so this is what we're going to do. Let's start by going to the class notebook today. I think we need to update the class notebook because we should have like 7 pages in there. Let's do this first. Okay, so I always make the table of contents be page 1. Some people are just not giving it a page number, and that's okay too. The important thing is that you have all these pages in there. I don't really care about the order, but I like to do them in the order we did them, So I would just have, sorry about the misspelling on season there. I would just have them like this. Oh, you know what? I'm gonna undo that, sorry. So page one's the table of contents. We actually did two different pages here. We did one for notes, season notes, and we did a different one. We did a different one for the seasons diagram, as I recall, because you just took notes right on the notebook page, huh? Eli, why don't you just take a picture of that and go? And then I put it on you to fill it in on your own time. Oops. Noise. I wrote noise instead of notes. It's so noise. And the last one on there is what we're going to do for the rest of the day. The last two pages, 8 and 9, are how we're going to finish class today. We're going to start by taking some notes from a few videos that come from Khan Academy. And then you're going to answer some questions along with a reading. So you should make this table of contents and then make a page for each of these and then insert the appropriate assignment. Number 8, we're going to take notes right in the class notebook again. Let's see, the last 3 things that I graded, 2, 3, have turned all 3 in. Go. Older than that, exactly. You all did the podcast, it's awesome. You guys are all caught up with the solar system stuff. It was like, at least if you did the moon phases, you haven't graded that one. You got some old stuff from climate. School that got school tomorrow? Saturday school?
No, I'm not Saturday school.
Unless you want to come in. Saturday school. Listen to a bunch of stuff. Totally improve your grade.
Alright. Yeah. I don't want to come in tomorrow or anytime. Unless I have
wonder
to.
why.
Unless I have to.
I'm getting paid. I wouldn't be here.
Yeah. So, I mean, I'll just do it during the week.
Marvin, you're missing a couple old climate things. And of course, anybody can still do retakes on the climate test. You turned everything in. There you go. let's get going on. Did you make all those pages? You got your class notebook table of contents all set up? Excellent. So we're gonna go do page, what was it, 8 right now on the videos? Or it said, measuring distances, notes, I think, huh?
Measuring distance in space.
Yeah. Well, we're not doing that quite yet. We are gonna do that. Right now, I want you to go to your class notebook. And I want you to have a blank page, and we're gonna take notes on that page from these 3 videos. No. They're not posted. I'm gonna play them up here.
I know what I'm going to tell. It's just about the moon.
No. Well, I mean, it includes the moon. It's about measuring distances in space.
Like after class.
Yeah. So, on the first section of your notes, the first video is called Scale of the Large. So, I would divide these notes into 3 parts. And the first of the 3 parts on your notes should be labeled Scale of the Large. You're going to take a few notes from this video. I'm going to stop it a couple times to mention some things. Same thing with the second and the third video. This one, Scale of the Large.
The purpose of this video is to just begin to appreciate how vast and enormous the universe is. And frankly, our brains really can't grasp it. What we'll see in this video is that we can't even grasp things that are actually super small compared to the size of the universe. And we actually don't even know what the entire size of the universe is. But with that said, let's actually just try to appreciate how small we are. So this is me. Begin to appreciate how vast and enormous the universe is. And frankly, our brains really can't grasp it. But the purpose of this video is to just begin to appreciate how vast and enormous the universe is. And frankly, our brains really can't grasp it. What we'll see in this video is that we can't even grasp things that are actually super small compared to the size of the universe. And we actually don't even know what the entire size of the universe is. But with that said, let's actually just try to appreciate how small we are. So this is me right over here. I am I am 5'9" depending on whether I'm wearing shoes, maybe 5'10" with shoes. But for the sake of this video, let's just roughly approximate around 6 feet or around roughly, I'm not going to go into the details of the math, around 2 meters. Now, if I were to lie down 10 times in a row, you'd get about the length of an 18 wheeler. It's about 60 feet long. So this is times 10. Now, if you were to put an 18 wheeler on kind of, if you were to make it tall as opposed to long, somehow stand it up, and you were to do that 10 times in a row, you'll get to the height of roughly a 60-story skyscraper. So once again, if you took me and you piled me up 100 times, you'll get about a 60-story skyscraper. Now, if you took that skyscraper and if you were to lie it down 10 times in a row, you'd get something of the length of the Golden Gate Bridge. And once again, I'm not giving you the exact numbers. It's not always going to be exactly 10, but we're now getting to about something that's a little on the order of a mile long. So the Golden Gate Bridge is actually longer than a mile, but if you go within the twin spans, it's roughly about a mile. It's actually a little longer than that, but that gives you a sense of a mile. Now, if you multiply that by 10, you get to the size of a large city. And this right here is a satellite photograph of San Francisco. This is the actual Golden Gate Bridge here. And when I copy and pasted this picture, I tried to make it roughly 10 miles by 10 miles, just so you appreciate the scale. And what's interesting here, and this picture is interesting because this is the first time we can kind of relate to cities, but when you look at a city on this scale, it's starting to get larger than what we're used to processing on a daily basis. This a bridge, we've been on a bridge, we know what a bridge looks like. We know that a bridge is huge, but it doesn't feel like something that we can't comprehend. Already a city is something that we can't kind of comprehend all at once. We can drive across the city, we can look at satellite imagery, but this is, if I were to show a human on this, it would be unbelievably small. You would you wouldn't actually be able to see it. It would be less than a pixel on this image. A house is less than a pixel on this image. But let's keep multiplying by 10. If you get multiplied by 10 again, you get to something roughly the size of the San Francisco Bay Area. This whole square over here is roughly that square right over there. Let's multiply it by 10 again. By 10. So this square is about 100 miles by 100 miles. So this one would be about 1,000 miles by 1,000 miles. And now you're including a big part of the western United States. You have California here, you have Nevada here, you have Arizona and New Mexico. So a big chunk of a big continent we're already including. And frankly, this is beyond the scale that we're used to operating. We've seen maps, so maybe we're a little used to it. But if you ever had to walk across this type of distance, it would take you a while. To some degree, the fact that planes go so fast, almost unimaginably fast for us, that it's made it feel like things like continents aren't as big because you can fly across them in 5 or 6 hours. But these are already huge distances. But once again, you take this square that's about 1,000 miles by 1,000 miles, and you multiply that by 10, and you get pretty close, a little bit over the diameter of the Earth. A little bit over the diameter of the Earth. But once again, we're on the Earth. We kind of relate to the Earth. If you look carefully at the horizon, you might see a little bit of a curvature, especially if you were to get into the plane. So you can even though this is frankly larger than my brain can really grasp, we can kind of relate to the Earth. Now, you multiply the diameter of Earth times 10, and you get to the diameter of Jupiter. And so if you were to sit Earth right next to Jupiter, obviously they're nowhere near that close. That would destroy both of the planets. Actually, it would definitely destroy Earth. It would probably just be merged into Jupiter. Earth. So if you put Earth next to Jupiter, it would look something like that, right? Right over there. So I would say that Jupiter is definitely on this kind of diagram that I'm drawing here is definitely the first thing that I can't comprehend. I mean, the Earth itself. itself is so vastly huge, Jupiter it's 10 times bigger in diameter. It's much more, it's much larger in terms of mass and volume and all the rest. But just in terms of diameter, it is 10 times bigger. But let's keep going. 10 times Jupiter gets us to the sun. This is times 10. So if this is the sun, and if I were to draw Jupiter, it would look something like, I'll do Jupiter in pink. Jupiter would be around that big. And then the Earth would be around that big if you were to put them all next to each other. So the sun, once again, is huge. Even though we see it almost every day, it is unimaginably huge. Even the Earth is kind of unimaginably huge, and the sun is 100 times more unimaginably bigger. Now we're going to start getting really, really, really wacky. You multiply the diameter of the sun, which is already 100 times the diameter of the Earth. You multiply that times 100, and that is the distance from the Earth to the sun. So I've drawn the sun here as a little pixel, and I didn't even draw the Earth as a pixel because a pixel would be way too large. It would have to be 100th of a pixel in order to draw the Earth properly. So this is a unbelievable distance that between the Earth and the sun. It's 100 times the distance of the sun of the diameter of the sun itself. So it's massive, massive. But once again, these things are relatively close compared to where we're about to go. Because if we want to get to the nearest star, so remember, the sun is 100 times the diameter of the Earth. The distance between the sun and the Earth is 100 times that. Or you could say it's 10,000 times the diameter of the Earth. So these are unimaginable distances. But to get to the nearest star, which is 4.2 light years away, it's 200,000 times, and once again, unimaginable. It's 200,000 times the distance between the Earth and the sun. And to give you a rough sense of how far apart these things are, if the sun was roughly the size of a basketball, if the average star was about the size of a basketball, and our part of the galaxy in a volume the size of the Earth, so if you had just like a big volume the size of the Earth, if the stars were the sizes of basketballs in our part of the galaxy, you would only have a handful of basketballs per that volume. So unbelievably sparse, even though the galaxy looks like, even though when you look at the galaxy, and this is just an artist's depiction of it, it looks like something that has, kind of the spray of stars and it looks reasonably dense. There is actually a huge amount of space that the great majority of the volume in the galaxy is just empty space. There's no stars, no planets, no nothing. I mean, this is a huge jump that I'm talking about. And then if you really want to realize how large a galaxy itself can be, you take this distance between the sun or between our solar system and the nearest star. So that's 200,000 times the distance between the Earth and the sun, and you multiply that distance by 25,000. So if the sun is right here, our nearest star will be in that same pixel. They'll actually be within, I mean, you'd have to get a ton of stars within that one pixel, even though they're so far apart. And then this whole thing is 100,000 light years. It's 25,000 times the distance than the distance between the sun and the nearest star. So we're talking about unimaginable, unfathomable distances just for a galaxy. And now we're going to get our, frankly, my brain is already, it's already well beyond anything that it can really process. At this point, it almost just becomes abstract, thinking. It just becomes playing with numbers and mathematics. But to get a sense of the universe itself, the observable universe, and we have to be clear because we can only observe light that started leaving from its source 13.7 billion years ago, because that's how old the universe is. The observable universe is about 93 billion light years across. And the reason why it's larger than 13.7 billion is that the points in space that emitted light 13.7 billion years ago, those have been going away from us. So now they're on the order of 40 billion light years away. But this isn't about cosmology. This is just about scale and appreciating how huge the universe is. Just in the part of the universe that we can theoretically observe, you have to get, and that we can observe just because we're getting electromagnetic radiation from those parts of the universe. You would have to multiply this number. So let me make this clear. 100,000 light years, that's the diameter of the Milky Way. So 100,000 light years, that's the diameter of the Milky Way. You would have to multiply it not by 1,000. 1,000 would get you to 100 million light years. Right? This is 100,000 times 1,000 is 100 million. You have to multiply by 1,000 again, by 1,000 again to get to 100 billion light years. And the universe, for all we know, might be much, 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 much larger. It might even be infinite. Who knows? But to get from just the diameter of the Milky Way to the observable universe, you have to multiply by 1,000,000. And already this is an unfathomable distance. So in the whole scheme of things, not only are we pretty small, and not only are the things we build pretty small, and not only is our planet ultra small, and not only is our sun ultra small, and our solar system ultra small, but our galaxy is really nothing compared to the vastness of the universe. And as we see, as we start getting into like the galaxy goal in this my goal in this video and the next few is to start giving a sense of the scale of really just the Earth and the solar system. And as we see, as we start getting into like the galaxy and the universe, it just becomes almost impossible to imagine, but we'll at least give our best shot. So I think most of us watching this video know that this right here is Earth. This right here is Earth. And just to get a sense of scale here, I think probably the largest distance that we can somehow relate to is about 100 miles. You can get into a car for an hour and a half and go about 100 miles. And on the Earth, that would be about this far. It would be a speck that would look something like that. That is 100 miles. And also to get us a bit of scale, let's think about a speed that at least we can kind of comprehend. And that would be maybe the speed of a so let's think of the speed of a bullet. Speed of a bullet. Maybe we can't comprehend it, but I'll say this is the fastest thing that we can maybe kind of comprehend. It goes about, and there are different types of bullets depending on the type of gun and all of that, about 280 meters per second, which is about 1,000 kilometers 1,000 kilometers per hour. And this is also roughly the speed of a jet So just to give a sense of scale here, the Earth's circumference. So if you were to go around the planet, the Earth's circumference, just like that, is about 40,000 kilometers. It is 40,000 kilometers. 40,000 kilometers. So if you were to travel at the speed of a bullet, or the speed of a jetliner, at 1,000 kilometers an hour, it would take you 40 hours to circumnavigate the Earth, 40 hours to go around the Earth. So it would take you 40 hours. 40 hours to go around the Earth. And I think none of this information is too surprising. You might have taken 12 or 15-hour flights that get you not all the way around the Earth, but get you pretty far, San Francisco to Australia or something like that. So right now, these aren't at scales that are too crazy. Although, even for me, even the Earth itself is a pretty mind-blowingly large object. Now, with that out of the way, let's think about the sun, because the sun starts to approach something far huger. So this obviously here is the sun. And I think most people appreciate that the sun is larger, that it's much larger than the Earth, and that it's pretty far away from the Earth. But I don't think most people, including myself, fully appreciate how large the sun is or how far it is away from the Earth. So just to give you a sense, the sun is 109 times the circumference of the Earth times the circumference of the Earth. So if we do that same thought exercise there, if we said, okay, if I'm traveling at the speed of a bullet or the speed of a jetliner, it would take me 40 hours to go around the Earth. Well, how long would it take to go around the sun? So if you were to get on a jet plane and try to go around the sun, or if you were to somehow ride a bullet and try to go around the sun, do a complete circumnavigation of the sun, it's going to take you 109 times as long as it would have taken you to do the Earth. So it would be 100 times, I could do 109, but just for approximate, it's roughly 100 times the circumference of the Earth. So 109 times 40 is equal to 4,000 hours. And just to get a sense of what 4,000 is, actually, since I have the calculator out, let's do the exact calculation. It's 109 times the circumference of the Earth times 40 hours. That's what it would take to do the circumference of the Earth. So it's 4,360 hours to circumnavigate the sun, going at the speed of a bullet or a jetliner. And so that is 24 hours in the day. That is 181 days. It would take you roughly half a year. It would take half a year to go around the sun at the speed of a jetliner. Let me write this down. Half a year. Half a year. The sun is huge. The sun is huge. Now, that by itself may or may not be spread. And actually, let me give you a sense of scale here, because I have this other diagram of a sun. And we'll talk more about the rest of the solar system in the next video. But over here, at this scale, this sun, at least on my screen, if I were to complete it, would probably be about 20 inches in diameter. The Earth is just this little thing over here, smaller than a raindrop. It's just a small little thing over here. If I were to draw it on this scale, where the sun is even smaller, the Earth would be about that. The Earth would be right about that big. Now, what isn't obvious, because we've all done our science projects in third and fourth grade, or we always see these diagrams of the solar system that look something like this, is that these planets are way further away. Even though these are depicted to scale, they're way further away from the sun than this makes it look. So the sun, sorry, the Earth is 150 million kilometers from the sun. So the Earth is, so this distance, if this is the sun right here, if this was the sun right here, you wouldn't even, at this scale, you wouldn't even be able to see the Earth. You wouldn't be able to see the Earth. It wouldn't even be a pixel, but it would be 150. It would be 150 million, 150 million, 150 million kilometers from the Earth. And this distance right here is called an astronomical unit. And we'll be using that term in the next few videos just because it's an easier way to think about distance. Sometimes abbreviated AU, astronomical unit. Astronomical unit. And just to give a sense of how far this is, light, which is something that we think is almost infinitely fast, something that looks instantaneous, that takes 8 minutes to travel from the sun to the Earth. If the sun were to disappear, it would take 8 minutes for that light for us to know that it disappeared on Earth. Or another way, just to put it in the sense of this jet airplane, let's get the calculator back out. So we have 100. We're talking about 150. That's 1,000 million. That's 150 million kilometers. So if we're going at 1,000 kilometers an hour, so if we go to 1,000 kilometers an hour, it would take us 150,000 hours at the speed of a bullet or at the speed of a jet plane to get to the sun. And just to put that in perspective, that if we wanted it in days, there's 24 hours per day. So this would be 6,250 days, or if we divide by 365, roughly 17 years. If you were to shoot a bullet straight at the sun, it would take 17 years to get there. If it could maintain its velocity somehow. So this would take a bullet or a jet plane 17 years to get to the sun. 17 years. Or another way to visualize it. This sun right over here, it looks on my screen, it has about a 5 or 6 inch diameter. If I were to actually do it as scale, this little dot right here, this little dot, which is the Earth, this speck, if I actually wanted to draw this distance at scale, I would have to put this speck about 50 feet away from the sun, 50 or 60 feet away from the sun. If you were to look at the solar system, and obviously there's other things in the solar system, we'll talk more about them in the next video, you wouldn't even notice this speck. This is a little dust thing flying around this sun. And as we go further and further out of this solar system, you're going to see even this distance starts to become ridiculously small. Or another way to think about it, if the sun was about this size, then this speck, then the Earth at this scale would be about 200 feet away from it. So you can imagine it if you had a football field. So let me draw a football field. These are the end zones, one end zone, another end zone. And if you were to stick something maybe the size of a medicine ball, a little bit bigger than a basketball at one end zone, this little speck would be about 60 yards away, or about roughly 60 meters away. So it's this little speck. You wouldn't even notice it on a scale of a football field, something this size. Anyway, I'm going to leave you there. Hopefully that gives you just starts to blow your mind when you think about just the scale of the sun, the earth, and how far the earth is away from the sun. And then we're going to see even those distances, even those scales are super small when you start thinking about the rest of the solar system, and especially when we start going beyond the solar system. My goal.
He was comparing his computer screen and how big that picture of the sun looked to a football field. But up on this screen, it's much bigger than that, huh? So what we were seeing, if the sun was that big around, it's more like three football fields away to get to the Earth. And then the Earth would be that little dot that he was showing. Okay, so that was number 2, scale of the Earth and Sun. Part 3 in our last video for today, scale of the solar system. So add some notes on part 3.
You off in the last video, I think we were getting a reasonably good appreciation for how huge the sun is, especially relative to the Earth, and how far the Earth is away from the sun. That most of these diagrams that we see when we in science textbooks, they don't give justice. In fact, when I showed it this sun over here that was about 5 or 6 inches across, I said Earth would be just this little speck about 40 feet. It wouldn't be this distance, it would be about 40 feet to the left or the right, or it would have a radius, its orbit would have a radius of about 40 feet. So it'd be this, you wouldn't even notice it if you were looking at this thing over here. It'd be this little speck orbiting at this huge, huge distance. If you look at this sun over here, if I were to draw the whole sun, it looks like it would have a diameter of about 20 inches. So in this situation, this Earth right here, this is drawn to scale, this Earth would not be anywhere near this close. It would be about 200 feet that way, or about 60 or 70 meters, 60 meters. So you could imagine if the sun was this size, sitting on something like a football field, this little speck of an Earth, this little thing right here, would be sitting on the other 40-yard line, 60 meters away. So huge, you wouldn't even notice it. You might notice this from a distance, but you wouldn't even see this thing over here. And the other planets are even further. Well, not all of the other planets. Obviously, you have Mercury. You have Mercury here. I think most of us are familiar with these, but I'll just list them here just in case. That's Mercury. This is Venus. Mercury is the smallest of the planets where it's not debated whether it's a planet. Pluto is the smallest, but some people debate whether it's really a planet or kind of just a large solar body or a dwarf planet or any of those type of things. But then you have Venus, probably the closest in size to the Earth, or it is the closest in size to the Earth. And then you have Mars, and then you have Jupiter. And just to give a sense of, once again, how far these things are, if I were to go back to the analogy of this being the size of the sun, then Jupiter is 5 times further than Earth. So this would be if I were to actually do the scale distance, this would be 300 meters away. 300 meters. So if I had a nice big, maybe medicine ball size sun right over here, maybe basketball size sun, a little bit bigger than a basketball, this looks on my screen, then I would put this little thing that's smaller than a ping pong ball, I would put this 3 football fields away. That's how far Jupiter is. And then Saturn's about twice as far as that. Saturn is about 9 times the distance. So let me make it clear. The Earth is 1 astronomical unit away from the sun, roughly. Its distance changes. It's not a perfectly circular orbit. Jupiter is approximately a little bit 5 plus astronomical units, so a little bit more than 5 times the distance of the sun to the Earth. And Saturn is approximately 9 astronomical units, or 9 times the distance from the sun to the earth. So once again, this would be 9 football fields away, or another way to think about it would be essentially a kilometer away. If we had a kind of a medicine ball sized sun, this little smaller than a ping pong balled Saturn would be a kilometer away. And I just want to really reiterate that because you never kind of visualize it that way. Because
Okay, so for comparison, if the sun was this size of a basketball, and here it is in my classroom, Saturn would be smaller than a ping pong ball, and it would be down at the beach. And it's so much bigger than the Earth, isn't it? Right? So these numbers and distances they're huge.
just for the sake of being able to draw it on a page, you see diagrams. You see diagrams that look like this, and they really don't give you a sense of how small these planets are relative to the sun, and especially relative to their distance from the sun. And then after Saturn, you have Uranus, and then Neptune, and then Neptune. And obviously these guys are even further. And just to give you a sense, it's very easy to start talking about galaxies and universes and all of or the universe. But I really just want to get, already what we've talked about, we're talking about huge distances, huge scale. We already talked about that it would take a jet plane 17 years to travel from the Earth to the sun. Multiply that by 5, about 100 years to go from Jupiter to the sun. 200 years to go from Saturn to the sun. So you could have had Abraham Lincoln get into a jet plane, and he still wouldn't have got, if he left from Saturn, he still would not have gotten to the sun. So these are huge, huge distances. But we're not done with the solar system there. Just to give a sense of scale. So this right here, that's the sun. And each of these planets are actually narrower than these orbits. So they just draw these orbits here, but you wouldn't actually even see the actual planets here at this type of a scale. But this is one astronomical unit right over here, the distance from the sun to the Earth. Then you have Mars. Then you have the asteroid belt. There you have the asteroid belt, which also has some pretty big things in it itself. And it has these things that are kind of considered almost dwarf planets, things like Ceres. You could look those type things up. And then you have Jupiter out here. And once again, we said it would take 100 years, or roughly 100 years, for a jet plane to get from Jupiter to the sun. But even if you take this whole box here, which is a huge amount of distance, of roughly about 5 astronomical units, it would take about 40 minutes for light to get from the sun to Jupiter. So this is a huge, huge distance. But even this huge distance, we can put it into this little box right over here. This little box right over here. So this whole box right over there can be fit into this box. And that you need to do that in order to appreciate the orbits of the outer planets. And so on this scale, the Earth and Venus and Mercury and Mars, their orbits look pretty much, you can't even differentiate them from the sun. They look so close. They almost look like they're part of the sun when you look at it on this scale. And then you have the outer planets, Saturn, Uranus, Neptune. And then we have a Kuiper belt. And this is more asteroids, but these are kind of more frozen, and when we think of ice, you always think of water ice, but out here it's so cold, and it's relatively getting dark now because we're pretty far from the sun, that things that we normally associate as gases are going to be in their solid form out here. So this isn't just rocky elements. This will also be things that we normally associate as gases, like methane, frozen methane. But even here, we're not done. We're not even out of the solar system yet. And actually, just to give you a sense of the scale we're operating right here, I have this chart right here from the Voyager mission. So the Voyager missions, Voyager 1 and 2, actually Voyager 2 left a little bit earlier, a month earlier. Voyager 1 is just traveling faster. They left about a year after I was born. And their current velocity, just to give you a sense of how fast, Voyager 1 right here. Voyager 1 right here is right now traveling at 61,000 kilometers per hour. That's about 17 kilometers per second. The size of a city every second. It's going that fast. That's, at least in my mind, an unfathomably fast velocity. This thing has been traveling roughly that fast. It's been going around planets and gaining acceleration as it went around orbits. But for the most of the time, it's been going at a pretty fast speed. And just to translate it to people who don't relate to kilometers, that's about 38,000 miles per hour. So this huge, huge, unfathomably fast speed. And it's been doing it since 1977. I was learning to walk, and when I was learning to walk, it was traveling at this super fast speed. And then when I was learning to talk, I mean, our whole lives when we're sleeping, everything we're eating, I'm in elementary school, it's still rocketing out of the solar system at roughly this speed. Its velocity's changed, but especially once it got outside of the planets, it's been roughly at this velocity. So it's just been rocketing out. And I don't want to say only, but it's gotten this far. It's gotten this far. It's gotten about, if we look at it on this scale, it's gotten about that far right there. It's about 115, 116 astronomical units.
You'd asked earlier how long it would take to get to the sun in a rocket, right? And now this is giving us better information, traveling at 38,000 miles per hour, right? Another example is we sent a probe called Cassini to Saturn. It took 6 years to get to Saturn, which was probably about 8 times farther than it is to the sun. So it would still take about half a year for a rocket to get to the sun. The other thing that's kind of cool on here, just in terms, I don't know if you guys heard of the Voyager spacecraft at all. Well, launched in the late 70s, they were initially planned to explore Jupiter and Saturn. And they're flying through space in a straight line. And unlike what we think is happening because of watching movies like Star Wars and TV shows like Star Trek, we don't have that much control over the direction that these things are moving. They have to go a long way in any one direction for a long time to get anywhere. And so what we end up doing is we use the planets to change their direction. So here comes Voyager towards Jupiter, and it's coming in to Jupiter and it's taking photos and stuff. And then Jupiter's gravity grabs the spacecraft. And if we don't approach it at the right angle, it will crash into Jupiter. But we've controlled it from here and designed it to kind of go past the planet, but then the gravity pulls it into a new direction. And we can arrange it so that when it gets curved by that planet, it'll head to our next target, like Saturn. And they ended up being able to see not only Jupiter and Saturn, but also Uranus and Neptune. They didn't even plan for that in advance, but by modifying its trajectory, and they had plenty of time for that, we were able to get more information from those spacecraft. Now, once they went past Neptune, they just kept going, and they're still going at 38,000 miles an hour out of the solar system. What is that? 40 years that's been going now?
And to give a sense, so there's two ways to think about it. One is like, wow, that's really far, because if we know that even on this scale, you can't even see Earth's orbit. So this looks like it's a pretty far distance. And just to give you a sense of how far 116 astronomical units are, if 2,000 years ago, Jesus got on a plane, I actually cut and pasted a copy of Jesus just for visualization purposes, but if he got on a jetliner at 1,000 kilometers per hour and went straight in that direction, in the direction that Voyager would only just now be catching up to Jesus. So this is a huge distance. But at the same time, even though it's a huge distance, especially relative to everything else we've talked about, relative to just even the outer reaches of the solar system, we're still talking in terms of a small scale. So that's how far Voyager is. And just to give a sense on this scale, so this whole box over here can be contained in this box. And when you look at this box, Voyager's only gotten about that far after traveling at this unbelievable velocity for over 30 years, for about 33 years. And just to give you an idea of these other things, Sedna right here is one of the, it's a reasonably large sized outer solar system object. It's one of the furthest objects that we know of in the solar system, and it has this very eccentric orbit. So it gets, I don't want to say relatively close, but not unreasonably far away, and then it gets really far away from the sun. But even Sedna's orbit. So if I were to look at this, so this whole box over here, can be contained right over here. So in this diagram right here, you wouldn't even be able to see. It would be like a speck how far Voyager has traveled in 33 years at 38,000 miles per hour. You would not even be able to notice. You wouldn't even notice that distance. And even though you can't even notice that distance, we still have the sun's influence. The gravitational pull is still attracting things to it. And this right here, we speculate that there's the Oort cloud, and this is where the comets originate from. And this is just a bunch of frozen, you can almost, frozen gases and ice particles and things like that. But this is kind of, we're starting to get to the outer reaches of the solar system. And this distance right here is about 50,000 astronomical units. 50,000 astronomical units. And just to give a scale, because you hear a lot about light years and all of that, light years are about 63,000 astronomical units. So if you go a light year out from the cloud, a light year out from the sun, you'll end up in the Oort cloud, the hypothesized Oort cloud. And just to give a sense, another scale, the Oort cloud is actually, most of the planets' orbits are roughly in the same plane. But this right here is the orbit of the planets. And once again, these lines are drawn too thick. They're just drawn the thinnest possible so that you can see them, but they're still drawn too thick. And this gets us all the way to the Kuiper belt. But all of this over here, so all the way out to the Kuiper belt, all the way out to all of the major planets. This is Pluto's orbit right over here. This is Pluto's orbit right over here. This whole diagram is only sitting in right over there. You can barely see it. This whole diagram is just that dot in this. And then you can see the Oort cloud all around it. It's more of a spherical cloud, and we think it exists. Obviously, it's hard to observe things at that distance. So hopefully that gives you a beginning sense of the scale of the solar system. And what's really going to blow your mind, if this hasn't blown your mind already, is that this whole thing's going to start looking like a speck when you even just look at the local area around our galaxy, and much less the galaxy as a whole, much less the universe as a whole. Anyway, I don't want to get, well, anyway, this is starting to get crazy. Where we left off in the last video, I think we were getting a reasonably good appreciation.
So download this assignment if you haven't already, measuring distance in space. So this will be page 9 in your class notebook. So what he was talking about, a lot of the diagrams that we see of the planets have the distance is distorted so that we can see the planet. Even if they're showing the planet's sizes compared to one another, even if they're showing those sizes correctly, they're not showing the distances correctly. This one's the opposite. It's showing the correct distances, but the sizes of the planets are way too big. You wouldn't even really be able to see them. But the first thing I'd like you to do is take a pencil and draw a line, or maybe not a pencil. Why don't we just use a line? And draw a line from the sun to the earth. And then label that as 1 AU. And that's what we call an astronomical unit, the distance from Earth to the sun, an astronomical unit. And it's about 100 million miles. It varies a little bit because we're not a perfectly circular orbit. The average is closer to 93 million miles, but it's pretty easy to just remember 100 million. So what we're going to do is there's a couple pages that I'm going to read out loud. While I'm reading, I would like you to highlight the important text as we go, and then we run into some questions at the end. Okay? So here we go. Highlight as I read. The distances between celestial objects are so mind-bogglingly vast that specialist units are needed to chart it. To express in miles the distance from Earth to the edge of the observable universe, for example, results in the unwieldy figure of 270 crazy gazillions of miles. Even using mathematical notation to shorten it to 2.7 times 10 to the 23rd, it's still so esoteric as to be almost meaningless. What space needs is really, really big units of measurement. So what are these different units for measuring distances in space? The first one is the astronomical unit. Now, in this diagram, once again, nothing is to scale here. The distance to the planets is not correct. They should be more spread out than that. The planets themselves are shown too big. So it just helps us see what's going on if we distort it. At any rate, here's the definition of an AU, of an astronomical unit. It is equal to the radius of Earth's orbit around the sun, or to be more precise, the average radius, since our orbit is elliptical. So again, if I was to draw that on this diagram, it would be the distance of Earth's orbit to the sun. That would be 1 AU. Well, this one, I don't think we need to draw it really on here because this one's not to scale, so it doesn't really show us how far apart these actually are. For instance, Jupiter should be 5 AU away from the sun. So I need to take this distance, 1, 2, 3, 4. Jupiter should be about over here in this corner. So they've packed everything in there just so it fits in the same image. And AU is defined as 149,597,000, etc. meters, or 93 million miles, a value officially set by the International Astronomical Union in 2012. Astronomers have been trying to calculate the distance from Earth to the sun ever since, in the 3rd century BC, Archimedes estimated it to be about 10,000 times Earth radius, or 63 million kilometers. So he was nearly halfway there. Not bad for someone who lived 2,000 years before the telescope was invented. Let's do this. Right here, where it says an AU is defined as, let's write down an easier way to remember it. So it was 93 million miles, but we can just round that off, I think, for our purposes to 100 million. Makes it a lot easier to work with. It wasn't until 1695 that Christian Huygens made the first close guess of 24,000 Earth radii, or 152 million kilometers, which is about 100 million miles. So he was pretty close. Some science historians dismiss his calculations as more luck than judgment, preferring to cite John Reacher and Giovanni Cassini's rigorously calculated 22,000 Earth radii, 140 million kilometers. And they think this was the first scientifically plausible estimate, even though they weren't quite as close as Huygens. But both of these guys were commemorated in the names of the spacecraft that went to Saturn. So I was talking about this Cassini spacecraft named after Giovanni Cassini, and it was launched from Earth in 1997, I think, and it went to Saturn. Here's the Earth. Now, if you're going to launch to Saturn, are you going to launch to the far side of the sun from the Earth? Do you want to have to pass that additional distance? Or do you want to launch on the same side of the sun as you? Right? You want to minimize that distance as much as possible. However, remember that we're both moving. So launching a spacecraft to Saturn is kind of like you're in a car going down the freeway and another car is coming the other way and you're going to try to toss them a ball. Right? They're moving, you're moving, and you got to calculate everything just right just to get there. And it took 6 years for the spacecraft to get from Earth to Saturn's orbit, which is that circle. But that's, again, not big enough. It should be 10 times bigger, the distance to the sun. It took 6 years to get there. It was named after Cassini. And when it got there, it had this landing craft that dropped onto one of Saturn's moons, and that landing craft was named after Huygens. These guys that first calculated the length of an astronomical unit. Okay, so that's our first measurement. Measurement number 2, light years. Now you got to be careful when you're thinking about light years because it has the word year in it, which is a measurement of time. But a light year is not a measurement of time. It's a measurement of distance. It's how far light travels in a year. So here's an image of a galaxy 130 million light years from Earth. That means it takes its light 130 million years to get to us. For the light traveling at the speed of light, it took 130 million years to get here. So when we look at it in a telescope, we're looking at light that left that galaxy 130 million years ago. Do we even know if it looks the same anymore? Maybe this whole galaxy exploded. Maybe it collapsed. Maybe there's been 10 supernovas in that time. I don't know. Maybe there's been 10,000 supernovas in that time. 130 million years is a long time. So we're looking at old light, and they call it look back time. We're looking back 130 million years in time when we look at this particular galaxy. Now let's turn this around. What if there was an intelligent race in that galaxy looking at Earth? If they look at us today, would they see you and me? They'd see what the Earth was like 130 million years ago. They would see dinosaurs walking around. That's how long it took light to get there from here. So let's highlight some more. A common method for measuring distance in space is to measure how far light travels in 1 year. Known as a light year, it's around 9.5 trillion kilometers. If you want to be precise, the International Astronomers Union regards a year as 365.25 days, which makes a light year 9.4 trillion kilometers. The germ of the concept originated with Friedrich Bessel, who in 1838 made the first successful measurement of the distance to a star outside our solar system, 61 Cygni. So this is the name of a star. The Cygni refers to the fact that it's in the constellation Cygnus, which you can see in the summertime. Cygnus the swan. 61 means that it is the 61st brightest star in that constellation. In his findings, he mentioned that light takes 10.3 years to travel from 61 Cygni to Earth. He wasn't seriously positing the idea of light years as a unit. For one thing, the speed of light at that time had yet to be calculated accurately. However, the concept was too enticing to ignore, and by the end of the 19th century, it was in general use, even if some astronomers ever since, including Arthur Eddington, who called it irrelevant, have been sniffy about the use of the light year. They're a little bit, what do I want to say? They think they're above the use of a light year. So why is the light year useful? Well, for example, take our nearest extrasolar star called Proxima Centauri. What's the closest star to us? The sun. So that's why they didn't say the closest star. They said the closest extrasolar star, the closest star beyond the sun. Proxima Centauri. Notice it has the word proxima, which means nearby, an approximation. It's proximate. And Centauri means it's in the constellation, the Centaur. It happens we cannot see this star from the northern hemisphere. It's like down there somewhere. So we never see Proxima Centauri. Instead of expressing the distance to Proxima Centauri in miles, which would be 38, what? 38 trillion miles. Or we could say it in astronomical units, it would still be 250,000 of those. These values are too big to really grasp. Instead, we say it's 4.25 light years away. It takes 4.25 years for that light to reach us. On the other hand, our closest neighboring galaxy is 2 million light years away. So Proxima Centauri is on the same galaxy as we are. It's in the Milky Way galaxy. But Andromeda, a different galaxy, which you can see naked eye if you look in the right part of the sky on a dark night in the wintertime, 2 million light years away to our nearest neighbor galaxy.
Wait, what galaxy are we in?
We're in the Milky Way galaxy. Okay, and our third measurement is called a parsec. And this one takes a little acting out. So what I'd like you to do is take your finger about this far away from your face and look at it through one eye. And have the back of the room behind you. So you can see something in the back of the room. Like I'm lining up the finger with that thermostat there. You want something pretty far away from you. So just choose anything to line it up with. Look at it with that one eye. Now don't move your finger, but switch to the other eye. Is the finger still lined up with that spot? Or does it jump from one spot to another when you wink from one eye to the next? All right? It jumps a lot, doesn't it? Now, take your arm as far away as you can and do it again. And how much does it jump when it's far away compared to when it's close? For me, when it's far away, it's jumping maybe that much, but when it's close, I see it jumping that much. So a closer object looked at from a different angle, from two different angles, my eyes, it moves across the background. And that's what they're showing in this diagram. Here's the background of the stars, and we're looking at this star from the Earth. But on this day, we see it here, and notice how it's in a different place. The yellow star is in a different place compared to the background stars. You see how it moves from one spot to another? Can you recognize the Big Dipper constellation there? And what's happening is if we look at this star 6 months apart, because the Earth is moving around the sun, it's just like us winking our eyes. We want to get as much distance as possible, so we measure it in June and then in December, for instance, 6 months apart. And then we can measure this angle, and that tells us how far away it is. Now, this whole thing about how it seems to move positions is called parallax. It's because it's not parallel. And then we measure this in seconds of arc, just like we measured angles in degrees, right? But when you break a degree into 60 pieces, you have seconds. And then you divide those by 60 and those by 60, and you get arc seconds. And that's what a parsec is. So if I go back to this diagram, the parsec is this distance between the star and the sun. Letter E is the parsec. But the way we measure it is by measuring these angles. Angle D here, the parallax angle. So a parsec is roughly 30 trillion kilometers, a little over 3 light years. Officially, a parsec is the distance at which one astronomical unit subtends an angle of 1 arc second. This definition would leave most people going, huh? But it's not quite as arcane as it sounds. The parsec is based on parallax vision. Notice they both start with PAR. For a practical example, hold your finger in front of your eyes, then alternate closing each eye. The finger appears to leap from side to side in relation to the background. Now imagine that on a cosmic scale. If Earth is on one side of the sun, when we look at a nearby star, it will appear to be in one position in respect to the stars in the background. 6 months later, when Earth is on the extreme other side of the sun, that same star will appear to be in a slightly different position against its background. We're talking about tiny amounts of difference, so we measure them in arc seconds, and there are 3,600 arc seconds in 1 degree of the sky. Your thumb at arm's length is something like 5 degrees. So it's a very tiny angle. So a parsec is the distance to the star that would appear to move by 2 arc seconds over a 6-month period. To put it another way, 1 arc second as Earth travels the linear equivalent of 1 astronomical unit. And this is where we get the name from. Parallax, arc second, a parsec. The term first appeared in a 1913 paper by English astronomer Frank Dyson. This places Proxima Centauri 1.3 parsecs away from us. And the Andromeda Galaxy is about 800 kiloparsecs. Hang on, kiloparsecs? Yes, even parsecs aren't huge enough for some scales, so they're upscaled to kiloparsecs, megaparsecs, and gigaparsecs, which will be 1,000, 1,000,000, or 1,000,000,000 parsecs, respectively. Which means we can now inform you that the edge of the visible universe is just 14 gigaparsecs away, without wearing out the 0 key on our keyboard. Yeah. When the bell rings, I want you to go get it and then bring it back. Okay, so here's a chart that compares these distances. We've got the astronomical units, the light years and the parsecs. The sun to Neptune, 30 astronomical units. A little further down, the sun to our nearest star, 58,000 astronomical units, and so on. So what I want you to do is go to page 5, and we're going to fill in this chart. Go to page 5. Across the top of the unit, across the top of the chart, I want you to give me those 3 units of measurement we just read about. Then you're going to describe them. Next, give me the distance in miles. How many miles is each of those units long? And then down here at the bottom where it says objects for which it's useful, basically you have 3 choices. One is for measuring the solar system, one is for measuring the galaxy, one is for measuring the universe. Remember, the solar system is just our sun and the planets around it. The galaxy is like an island of stars in space. Our galaxy is the Milky Way galaxy. We're just one of a million stars in that galaxy. But then the universe has all the galaxies. So I'd like you to get that filled in before the bell rings. So refer back to the reading to find the names of those things, to be able to describe it, and so on. So again, that last row, you just need to tell me which of those things goes with which measurement. What were our three measurements across the top? Astronomical unit, parsec, and light years. So describe them, find where it says how many miles they are. Maybe use the chart on page 4, might help you with that. Then tell me which objects they'd be useful for measurement. And if you don't finish in the next couple minutes, this is your homework.